looked at the three probability axioms. Now we want to look at some propositions that can be derived from these axioms. So now let's look at some propositions that can be derived from the probability axioms. Before we look at some propositions, let's look at the difference between axioms and propositions. So now propositions are true statements. Though they are true, but you have to prove axioms and you have to prove propositions. When you look at axioms, we said we take them as is, right? We don't question the validity. All concepts are based on these axioms. So, we basically believe them as is. We don't question the validity. Everything else builds on them. Now, propositions are also true statements, though they are true, but you have to prove propositions. Like, they are true statements, but you have to prove them before you believe they're true. So they do have to be proved. Unlike axioms, axioms you believe as is, you don't question the validity, but you do have to prove propositions before you believe. So axioms and propositions both are true statements. Both are true statements, but propositions need to be proved and axioms help us prove them. We accept axioms as is, we don't question the validity, we use them to prove propositions. Propositions need to be proven and axioms help us prove them. Right, so now let's look at the first proposition that we're going to look at. It is going to be, the first proposition is that probability of E complement is 1 minus probability of E, which is a complementary. The idea is that probability that this basically says that the probability that an event does not occur is 1 minus, so in words, this is what it's saying, is 1 minus, so in words, probability that an event doesn't occur is 1 minus the probability that it does occur. Now, like we said, propositions have to be proven and use axioms to prove them. So now let's look at a proof of this proposition. So now by axiom 2, now recall what axiom 2 was. It was probability of sample space is 1. By axiom 2, we know probability of sample space is 1. Now, E and E complement are collectively exhaustive. We know the collectively exhaustive events, the union is equal to the sample space. When we were looking at collectively exhaustive and mutually exclusive events, we talked about how an event and its complement are collectively exhaustive. Collectively exhaustive because whatever is not inside E, because whatever in the sample space is not inside E, it will be contained inside E complement. A collectively exhaustive. So S is equal to E union E complement, and thus we know E and E complement are collectively exhaustive, right? Because see, they are collectively exhaustive because if we see through a Venn diagram, this is the sample space, this is E, then this is E complement, right? They cover the entire sample space. The union is equal to the sample space. That's what collectively exhaustive events are, right? Sorry. So yeah, and thus we know the probability of E union E complement is equal to 1 because what is E union E complement? It's the sample space. Collectively exhaustive events are those that the probability of the union is the sample space. Now, since E and E complement, we already talked about an example of events which are both collectively exhaustive and mutually exclusive are event and its complement. An event and its complement are mutually exclusive. They don't contain any common outcomes. They cannot occur at the same time. The intersection is a null set. And they're collectively exhaustive as well, right? So we're using two facts over here that an event and its complement are mutually exclusive as well as collectively exhaustive. Are mutually exclusive. Mutually exclusive means the intersection is a null set. Applying axiom 3, axiom 3 was that if you have mutually exclusive events, the probability of the union is the sum of the individual probabilities. Now, since they're exclusive, so I can write probability of E union E complement is probability of E plus probability of E complement is 1. And from here it follows that probability of E complement is 1 minus probability of E. So we can prove this using axiom 2 and axiom 3 along with the fact that an event and its complement are collectively exhaustive, which means a union is the sample space and the event and the complement are mutually exclusive, which allows us to apply axiom 3. So now the proposition is that the probability of the null set is 0. This is very simple to prove. Now, since the null set and S are complements, so they're complements of each other, null set and the sample space are complements. So if I just let E to be S in proposition 1. So in proposition 1, right, in proposition 1 that we looked at, we said that probability of E complement is 1 minus probability of E. So if in proposition 1 that we just proved right now, if we just let E to be equal to the sample space, then probability of E complement, which is probability of null set, probability of S complement, because we're taking E to be the sample space S. So probability of S complement, which is just the null set, is 1 minus probability of S. And probability of S, we know. And by axiom 2, probability of sample space is 1. So, sorry, sample space is 1. So probability of null set is 1 minus 1 is 0. So in this way, we can prove these two propositions using our axioms.